This is session 9 for Models in Epidemiology and Biostatistics. I'm Gordon Hilton Fick. Well, for this session, we're going to be dealing with issues that are not directly about interpreting the quality of a model. The first 8 sessions, frankly, have been dominated by how can we take a model, the ingredients of the model, the regression coefficients, the fitted values, and interpret them in a way that fits with the science, that fits with the epidemiology, that fits with the ingredients that are important to conducting sound health research. There are some characteristics that I have left until now, and they are important. There's no doubt about it. But I want to say at the outset, and I'll be repeating this more than once, I think, that these characteristics are not, in my opinion, as important as the ingredients that we've discussed, the crucial issues of interpretation. If there's any one single focus to this series of presentations in models in epidemiology and biostatistics, it's about the quality of interpretation of a model. Nevertheless, let's now begin with the assessment of some of the other issues that come into the assessment of a model and its fit. So I'm going to start with a separation of projects into 2 types. May seem a little bit awkward in a way, but I think that early on in this session, I think you'll appreciate why I think it is important to make this distinction. So some of the models that we have looked at have a fixed set of distinct fitted values. And those were the kind that we saw early on with the models that deal with stratified analysis. Then there's a second type where, in fact, every individual or participant in the study will obtain a different fitted value. And one of the most obvious examples of that is where we have models in which we have a measured explanatory variable, and we have actual height, actual age, and they are not grouped. So in particular, we have a person's age, say in days, a person's height very accurately measured. So there isn't actually any grouping at all, except by just coincidence. So let's have a look at the first type, in which models have a fixed set of fitted values. And in order to do that, we'll return to a circumstance we saw very early on. That is a series of 2x2 tables described in a stratified analysis, i.e. with 4 strata here for this illustration. Age with 2 levels, young and old. Gender with 2 levels, female and male. And what do we see? Well, in fact, such a set of 4 2x2 tables determines precisely 8 estimates of conditional probabilities. These estimates being the proportions that we get in each of those categories. This could be, for example, using Stata set up with this very simple table command. So what do we mean here? Well, let's take a look at a simple analysis, a simple example. Let's suppose we have a study of a disease exposure relationship, and we have then the 4 strata by age group and by gender. Okay, now we can then interpret these results, and we have done examples of this in our work. But let's just explore, for example, here that we could have just taken the disease exposure relationship proportions and computed them. And here they are. There's only 8 groups, and we have numbers, meaningful numbers in each of those 8 groups. And so you can see we have 8 proportions. So what is this? Well, this is the proportion with the disease among those who are young and female and not exposed. And you can see that of the numbers in our data, we got approximately 60% were exposed. Okay? And you can see there's other examples. For example, amongst the old men, for example here, we can see the proportion that have disease is 0.619 for those who are exposed. There are 8 observed, if you like, proportions, and they are estimates of the 8 conditional probabilities that are in this investigation. Well, we could have established a model for this log of odds of disease, as we have seen many times here. We would then get a model, if we started, as has been our way, to begin with the model with 8 unknown regression coefficients, including the constant. And this gives us then fitted values for the log of the odds. Now, in this instance then, this model gives us 8 different fitted values for each of the distinct combinations of exposure, gender, and age group. Okay? Even though it looks like there's a lot more in play here, this model, in fact, only gives us 8 different fitted values. And here is the results from that logistic regression. And you can see then that we get some pieces here that we would like to study, perhaps. Let's leave the interpretation of this particular fit for the moment. Rather, let's compute, as we can do it with Stata, is construct the fitted values on the log odds scale and the fitted values on the probability scale. And you can see there's 2 possibilities here. Okay. To construct the fitted values on the log odds scale, we use the option XB, and to get the fitted values on the probability scale, we use the option P. Further, we'll also save the ingredients for, as we've done earlier, for a likelihood ratio test, which I'll be showing you a little bit further along here. Okay, so what do we get? Well, it turns out, yes indeed, we do get the 4 different fitted values on the log odds scale. Indeed, we get the 4 different values, or not 4, 8, the 8 different values on the log odds scale. And here we get the 8 different fitted values on the probability scale. There they are. Now, if you go back to that table of the observed proportions, you will see that these numbers, these fitted values, are identical to the observed proportions. So the fitted values from the model are the same as the observed proportions. There are 8 regression coefficients here, and these coefficients can be used to construct 8 conditional probabilities. Okay. There's a bit of math behind why this works. but I think it's fairly intuitive here. We have constructed a model with room for 8 things to be studied, and there are only 8 things we can. These 8 conditional probability estimates. Okay. Then it turns out, and we use this language a fair bit in epidemiology and biostatistics, any model that's nested within this model will inevitably yield fitted values that do not produce the observed proportions, at least not exactly. In other words, if we have fewer terms in a model than 8, then in principle we would not reproduce the observed proportions anymore. Well, what have we been doing earlier in these sessions? Well, we've been using the likelihood ratio test to compare the quality of 2 models. More specifically, we've been using the likelihood ratio test to perform tests of significance based on the number of regression coefficients that are in one model compared with another. Okay. But this whole process can be viewed as an assessment of the quality of the fit, insofar as we're comparing the fitted values. We could do so in lots of ways, not just likelihood ratio tests. We could construct graphs for them. We could have other characteristics that we might want to study. For example, if one or more of the fitted values seems out of place. Lots of different things we might entertain here. So let's then suppose that we decided to construct the model that does not have the GAE term. Okay. So we're going to then have this model. This is a model that's nested within model 1. Okay. And what do we see here? Well, again, we could spend a bit of time interpreting these estimates of the regression coefficients. And I would encourage you to do so. And once we've set up most of the ingredients here, we'll go back and do that. Okay. So let's construct the fitted values from model 2 now on the probability scale, and also save the ingredients that would be needed to perform a likelihood ratio test. Okay? So let's have a look. So if we compare the fitted values that we got from model 2 with the fitted values we got with model 1, if you give them some consideration, you can see that in fact they're pretty close. The fitted values we got from model 1 are very close to the fitted values we get from model 2. In fact, we can directly compute the differences between the fitted values from the first model and the fitted values from the second model. And what do we see? The differences here are small. So that says that the fitted values obtained from model 2 are close in some tangible way, right? They're close to the observed proportions, because the observed proportions are what we get in the model 1. Okay. So that would say that on the face of it, at least, from the point of view of the fitted values, there's very little difference between model 1 and model 2. And insofar as model 1 is exactly reproducing the fitted value, the observed proportions, and model 2 is coming very close to reproducing the observed proportions. So here you've seen what is often referred to as the residuals, the differences between the observed and the fitted. Often widely seen. Perhaps you've seen a bit of this earlier in your in your study of epidemiology and biostatistics. But what we can see is that the differences between the two sets of residuals are small. Okay. So again, just to repeat, we're suggesting that there's very little difference on the basis of the fitted values for choosing between Model 1 and Model 2. Okay. Now let's consider Model 3. Model 3 will exclude the term GA that we had in Model 2. Okay? And again, you could, and indeed I believe you should, spend a bit of time taking a look at these estimates of the regression coefficients now in the setting in which we have, what I have been calling earlier, an additive model, right? Okay. And I'll remind you that these things can be interpreted using the phrase assume common. Okay? All right. Let's now do the same thing we did before. Let's save the fitted values on the probability scale and also save the ingredients of Model 3 for the purposes of constructing a likelihood ratio test, which we're going to do in a little bit. Okay? All right, now we can compute or display the fitted values from the third model. And what do we see in this instance? What we get is fitted values that are very different from the fitted values we got with Models 1 or Model 2. Indeed, the differences you can see are they're substantial. These are differences between estimates of probabilities, just to remind you. So these numbers are big. The differences are big. Okay. Now let's consider the assessment of these three models with regard to their fitted values. So we see the residuals comparing Model 3 with Model 1 are large. The residuals comparing Model 2 with Model 1 are much smaller, very tiny. Now, as I said earlier, what we could do, and indeed we should do, is make our primary assessment of these models based on the epidemiology. But for the moment now, let's just suppose that we're going to just have a look at the numerical characteristics now, based on the fitted values we got from these three models. So as I said, the likelihood ratio test can be interpreted as comparisons between the fitted values computed from two different models. Okay? And if we do so, what do we see? If we compare, for example, the likelihood ratio test for Model 1 versus Model 3, we get a very low p-value, indicating a big difference between the parameters, the regression coefficients that were excluded in Model 3 compared with the characteristics that were in the regression coefficients that were in Model 1. Okay? So you'll remember that in Model 1 there were 8 regression coefficients, and in Model 3 there were 4. So the likelihood ratio test here has 4 degrees of freedom corresponding to the difference between the number of unknowns, of parameters in these models. But it's omnibus, isn't it, this particular likelihood ratio test? Nevertheless, it's saying that Model 1 is preferred to Model 3. Okay? On the other hand, if we were to do the same thing, comparing Model 1 with Model 2, and you'll recall that what we saw in that instance was that the fitted values in Model 1 were almost the same as the fitted values in Model 2. And the likelihood ratio test essentially duplicates that observation. Okay? There are only 3 differences between, there's 3 regression coefficients in Model 2 that have been removed compared with model 1. Okay, so the likelihood ratio test has 3 degrees of freedom here and is not significant. That's saying that on the basis of the comparison between the fitted values, there's nothing to choose between model 1 and model 2. Okay? Okay, before we go to the example, another example, this one that I'm going to come to next, study of heart disease and smoking, I'd like to go back and just take a few minutes with the models here. So what did we see here? The model with all 8 terms gave us this, right? We looked at the fact that there were 3 regression coefficients here associated with modification by gender and age. Okay? So these 3 regression coefficients, these numbers here, are addressing whether or not there's age or gender modification. And you'll remember that's something we could have proceeded with in a more gradual way. We could have, for example, just excluded the term EGA first and then refit, and so on. We've done that. But for now, let's just look at the fact that this particular model, with these 3 characteristics included, would suggest that there's modification. And there's modification by age or gender or both. If in fact these numbers were low, they're not. So what do we see? If we were to consider just a single comparison here, an addressing of these 3 p-values all at once, we would say, at least provisionally, there's no evidence of modification by either age or gender. Okay? So that would then be an argument for the study of model 2, which excludes the terms addressing age modification here, age or gender modification. This is the model that we would use to address or begin an assessment of whether or not age or gender confound. Okay? Because this regression coefficient here, we would interpret as the adjusted log odds ratio after adjustment for gender and age. And what did we see? We saw that when we compared model 1 with model 2 with the likelihood ratio test, we saw no material difference. Okay, remember that likelihood ratio test would be the one that we would often contemplate, right, if we wish to assess in an omnibus way modification by either age or gender. And we've done that. Okay. Then when we came to the additive model, we saw that, in fact, that we got a quite different message. The additive model, or the model that did not include all of the terms needed for proper adjustment for age and gender, did make a meaningful difference in the quality of the fit. Now, we could, and perhaps we should, view whether or not the comparison between model 2 and model 3 addresses an identification of confounding by either age or gender. And that would be a comparison of this number, 0.61, with the one we got in the previous model, where we got a quite different number, right? The number minus 0.05. Okay. So what we can see, and I won't be proceeding with all the details here, but that what we can see, here is that insofar as we're concerned that age or gender may confound, we see that comparing model 2 with model 3 clearly tells us something associated with confounding is going on. So we could consider the models with just age alone adjustment, with just gender alone adjustment, and the crude. We won't do that here. But my point here is that model 2 would be the definitive one for the assessment of confounding here. And insofar as we've compared model 2 with model 3, we have seen those regression coefficients associated with the log odds ratio are different. The two adjusted odds ratios there are different. Right? That's an argument against the additive model based on the epidemiology, and a preference for model 2 here. Now, it does also, you could say in somewhat of an important way, we can note that model 2 and model 3 are also different. Now, you'll notice here I have not provided the likelihood ratio test comparing model 2 and model 3. Now, that could be done, but its interpretation would not be addressing confounding here. Remember, confounding is about addressing whether or not regression coefficients change with the presence or absence of terms. Okay, the likelihood ratio test would be comparing the quality of the fit here, and would be comparing model 2 with model 3, and not per se what we're interested in addressing here. There's a fair bit in play here. If in fact we had not seen any confounding associated with either age or gender, then the selection of the fit might be directed by the fit that gave us the soundest set of fitted values. Okay? In other words, it could be that even though neither age or gender confound, that we still might argue for the inclusion of age and or gender in such a model. Okay, that's kind of reprising some things. But notice the likelihood ratio tests that are in play here are not really the primary things here. Nevertheless, except when comparing, for example, no, I shouldn't say that they're not important, but the likelihood ratio tests are dealing with the quality of the fit, right? And not per se with the test of the null hypotheses in play here. You might argue, oh, Gordon, you're just talking about the same thing. Sometimes I am, and sometimes I'm not. Remember, the assessment of by means of epidemiology in the determination of confounding is not based on the test of significance. Okay. And would not be based on the likelihood ratio test in this instance. Okay. All right. Now let's move to a second illustration of the issues that are in play here. Here we have a study, fairly large study, in which there were a fair number of individuals that whose age at entry was measured, and then their age when the study was conducted. So their age at entry was measured, and their date of birth was measured, and so an accurate measurement of their actual age could have been determined. But for our purposes here, we'll suppose that we only had the integers between 39 and 59. In other words, we'll assume that they took the actual ages and then assigned them to these groups in the correct way. So we now have 21, a lot of them, we have a lot of groups, but we have 21 age groups, okay? So we could, in principle, conduct a stratified analysis here of the relationship between coronary heart disease and smoking status, stratified by age. And if we did so, we get a very wide range of odds ratio estimates here. You can see these 21 numbers are not the same. And we might be concerned. On the other hand, you might say to me, wait a minute, there's a lot of overlapping of confidence intervals. Also true. And we might also provide a test of significance. I've not included it here, which would have a lot of degrees of freedom that would be testing for modification by age, omnibus. And we could have also maybe ruled out, or at some point, any discussion of modification by some means. And then looked at confounding here, and what we see is no evidence. The crude and the combined, the crude and the adjusted are very close. Okay, so how about we proceed with a consideration of a model-based analysis here, okay? We've got a fairly large number of odds ratios, and many of them are larger than one, yeah. And as you can see, some of the larger odds ratio estimates are in the intermediate ages. Okay, maybe it's an issue for us. Okay, so how about the corresponding logistic regression that corresponds to the stratified analysis we just did? Well, that's pretty easy to do with these double hashtags, which includes all of the terms that we might want. Okay, and there they are. And I've deleted some of them because, well, for this slide, it's already busy enough. Okay, quite a number of characteristics in play here. Now let's consider a plot of the fitted values that we would get from such a fit, from such a model and fit on the log odds scale. The fitted values, here the observed log odds versus age, okay? And what we'd like to do is try to get a handle on the nature of the relationship between the log odds of heart disease here and age, separately for the smokers and the non-smokers. Okay, and now we're going to get that from the right kind of display. Okay, how would we do that? Let's have a look. Well, there's all the fitted values. Okay, and you can see that I've used little boxes for the non-smokers and then little diamonds for the smokers. It's kind of hard to see what might be going on here. Maybe you might think, oh, well, there's something like an upside down U here, maybe, and perhaps maybe something more like an upside down U here. You might be saying, oh, that's pattern recognition here. A whole area of active research too. What do I do here to understand what patterns may be present in such a complicated visual? Well, the most widely seen in this type of work is using what are called smoothers. The most well-known smoother, arguably, to my knowledge at least, is something called low S. How it's computed, we're going to leave that all aside for the moment. But instead of displaying the actual values here, the actual observed log odds that have been estimated, let's look at the smoothed versions of these. So we're trying to get at what the signal is and remove the noise. That's some of the lingo that's sometimes used here. Okay, we've got two curves. What do they look like now? And here I'm giving away the finding. But if we do so, the two smoothers in this instance give us, as I kind of indicated before, maybe something that's sort of upside down U for the smokers, and maybe something that's sort of right side up U for the non-smokers. Okay. So what are we getting? Well, you might say visually at least, we're getting an indication of nonlinearity here, and that the form of the nonlinearity depends on whether you're in the smoking group or in the non-smoking group. Right? So you could see that what I have shown you here isn't per se based on the epidemiology. It is in fact more directly based on taking the fitted values we got from this particular model and attempting to gain some understanding. You can see where we're going with this, though. If we were to try a model that, say, allows for a simple form of nonlinearity, here we'll use the two parabolas, one for the smokers and one for the non-smokers. What do we see? Aha, we get evidence that there is nonlinearity, but the form of the nonlinearity depends on smoking status. That's what this p-value is getting at here. Okay. This is, the curvature is different for those who are smokers compared with those who are non-smokers. And what does the visual look like now? Well, then we get this particular display. This is a phenomenon seen fairly often, actually, in health research. Differing forms of nonlinearity. It would appear that the implication for smoking status depends, this vertical distance between these two curves appears to be most important for the intermediate ages, not for the younger ones in the study, and perhaps not for the older ones in the study. Okay. And it's of interest here that I could have, to aid with the interpretation of that model, is add standard errors and confidence limits to the that display we just saw. The computation of the standard errors is available with Stata, and also then we can then directly compute, say, 95% confidence limits, okay, point-wise. All right. And if we do that and then we graph it again, well, then we get some indication of, here are the confidence limits for the smokers, here are these two curves, and then the confidence limits for the non-smokers, they're down here. And what do we see? Well, the confidence limits, point-wise, don't overlap for the intermediate ages, roughly from the person's about age 43 until about age 54, roughly here, see? So that might help us, again, with understanding the implications of smoking status and the relationship between coronary heart disease and smoking and age. Okay. And we could then, if we wished, we could actually get a display that's in the probability scale. So those previous two displays were on the log odds scale, which isn't perhaps as widely seen or published in manuscripts, but such a display for the estimates of the probabilities is perhaps seen more often. And then you get a very similar looking message. So now we've got the estimates of the probabilities on the vertical scale and then the ages. And again, we see that the confidence limits on the probability scale, they don't overlap for the intermediate ages. And that is saying the same thing as we saw before. Just getting a somewhat more elaborate looking display, but maybe. But on the other hand, maybe the kind of one that one could speak to, say, either in a manuscript or in a presentation. All right. All of what I have done so far in this session is provide you with an instance in which An instance in which, in principle, we could have computed a fitted value for a fixed set of persons. We saw that in both of the illustrations. A vastly more common circumstance in health research studies, in epidemiologic studies, is where everybody has their own unique set of conditions, that there are no groups. Okay? So everybody has their own distinct fitted value. And it could be because we're measuring actual age here. Okay. Here, the residuals are of far less immediate value. Because what are we doing now? Well, it turns out we're going to be comparing. Oh, I got a little typo here. That should be up in here. This p hat should have been moved. Anyhow, the point is, here the observed fitted values, or the fitted values we get, will give us these p hats, but in every case, the observed proportion isn't really a proportion. It's just either a 0 or a 1. And so the difference between observed, which is 0 or 1, and fitted gives us these two things, right? You know, gee, they kind of got moved in my display here. They should have been there and there. Anyhow, I guess I could go and fix that, but I hope you can all see. Notice then we're really just looking at two sets of fitted values. The fitted values for those for which they do not have the condition, the disease, and the fitted values for when they do. The fact that in one case we're taking 0 minus p hat, and then in the second case we're taking 1 minus p hat, doesn't really help us much. But what we can do sometimes is look for anomalous or problematic fitted values. There's no simple way of gaining value from the displays we saw where there was an observed proportion in every determined group. If the observed proportions are all just zeros or ones, we don't get that same ability. That is a circumstance that's often misunderstood in the graphical display of residuals. That the graphical display of residuals in the setting where each individual determines their own set of conditions, many people will stare at that display with a mystified look, and the answer is, well, there isn't much per se to be gained from the direct study of those residual plots. It's also true. On the other hand, in some investigations, one can, in fact, determine, say, fitted values that just don't seem right. And in a later session, we'll be looking at an example to illustrate some of those issues. Maybe it's worth pointing out here that a whole area of here, it's not really that new anymore. It goes back to very important pioneering work done by Trevor Hastie and Rob Tibshirani. And that is the construction of generalized additive models. This, again, giving us the ability to directly compare fitted values from models for which a certain class of smoothing is being used rather than a more structured, perhaps, approach with linearity and so on. Okay. So with this approach, we end up with a so-called generalized additive model, which may include regression coefficients in the usual sense for a certain set of explanatory variables, the x's, but we use things called smoothers for another set of explanatory variables, the y's here. So, unfortunately, Stata does not yet, to my knowledge, have an implementation that's directly usable to use generalized additive models. But R most certainly does. That's an area where there's quite a bit of difference. And the assessment of nonlinearity done in this setting can be done with considerable advantage. Now, there's also been competing models discussed, models to compete with the merits for generalized additive models, and that's another topic, not for this session, but one that will come up as we proceed through in later sessions. Okay. So where am I going with all this? Maybe it seems a little bit scattered, and perhaps it is. But my point about the interpretation and study of different models in epidemiology and biostatistics is that the number one issue is a clear understanding of disease exposure relationships and the identification of modifiers and or confounders and other important explanatory variables. Now, what is also true is people will use terminology like prediction or forecast or looking to the future. In other words, trying to predict a person's outcome based on their explanatory variables. And in this instance, this notion of prediction or forecasting, some authors argue can be based on some of the things that we've discussed here so far, and we will be discussing moving forward in this session. In other words, it is the quality of the fit that one might argue that dominates one's attention insofar as we wish to obtain reliable predictions. Okay, and so the quality of predictions can be viewed as a primary objective of the use of models, and not per se on whether or not such a model provides us with the ingredients that are discussed in number one here. Okay. So logistic regression gives us estimates of log odds and estimates of probabilities. Now we could ask, okay, well, how do I go from these estimates that I have of probabilities to a prediction? Well, predictions are, yes, I think a person might well have disease in the future, or the prediction might be, no, they don't. In other words, we're going to be going from a probability estimate to a 0 or a 1. No, they don't. Yes, they do. Okay. And the argument then is, well, we would take the results from this model that gives us all these estimates of probabilities and establish some kind of a threshold. And then we would say, well, for individuals who have a probability estimate that's above the threshold, we would then say, all right, I'll predict they will have the outcome. And if the probability estimate is below the threshold, then we would say we would predict that they do not. The absence of the outcome here. Okay. Okay. Then we could compare the actual outcome with the prediction. We could ask, okay, we've got two sets of probability estimates, one's for those who had the heart disease and those who did not. And what would we want if we're thinking of the model as doing its job well as far as prediction is concerned? Well, we would hope that our probability estimates would be high for those persons with coronary heart disease, and the estimates would be low for those without coronary heart disease. Well, inevitably, it's going to be an imperfect picture, right? No matter how worthy the model, we're not going to have exactly what we might want. We're going to get something that's, we hope, will be decent, but we can't expect the world, perhaps. So, what do we do about this threshold then? The threshold that we might want to use for determining which probability estimate's high and which probability estimates are low. Well, one argument could be made that you should choose such a threshold based on the prevalence. Okay? The prevalence of coronary heart disease in this study population, if you have something that you feel is reasonably reliable. Well, it turns out that for this study, the prevalence was a bit more than 8%. So we could argue that, well, if I didn't have the model, if I didn't have any knowledge of the person's smoking status or their age to determine a prediction, I might just use a statement that roughly 8% of individuals in such a study will have coronary heart disease. But it doesn't really help us directly without the model, right? Okay, so once we have a model and the fitted values, the estimates now, from such a model, we're going to have a range of fitted values. Okay. And we could then argue that if an individual's fitted value is above, say, the prevalence, we would say, okay, let's classify them as having disease. And if the fitted value for that person is below that threshold, we would say, let's classify them as not having a disease. Okay? And you could argue, well, should we be using this number, 8%? You could see that, well, in fact, we have a fairly wide confidence interval for this prevalence estimate. All right, the standard error is not zero, whatever. The point being here is that a number around 8% seems like a pretty sensible number to be using as a guide. And we might also want to try other thresholds just to see. You can maybe see where I'm going with this. Thanks for your indulgence, or your patience with my indulgence, I guess. So in Stata, there's a post-estimation command, estat, that would give us the ingredients that we might like to see. We are going to get estimates of the sensitivity and of the specificity based on this particular threshold. So in particular, we can see that amongst those who do indeed have disease, that is this group, the 257, we correctly classified 163 of them if we were to use this argument based on their fitted value and this threshold, and that we could see gives us an estimated sensitivity of about 63%. Further, we could do the same thing with those without disease, without coronary heart disease, and there we would see we've got quite a large number of individuals that were in this study who did not have disease, right, of course. And the particular model with this cutoff gave us a number of 1,739 that were classified as not having disease. And so we can see that ratio gives us an estimated specificity now of just a bit over 60%. Okay. Sensitivity and specificity then. In these session 9 materials, there's a review of sensitivity, specificity, positive predictive value, and negative predictive value. If you're a little bit uncertain about these matters, I would refer you to that document, which was adapted from an important paper of Martin Bland's from a few years ago. Okay. So we saw that, in fact, we could have constructed estimates of the sensitivity and specificity. And in fact, because they are estimates of probabilities, we could have constructed confidence limits for them, right? We could see, okay, this number this sensitivity number has this range of plausible values based on confidence limits, right? Similarly, for the specificity, we get an estimate of the specificity and a confidence interval for the specificity, which in this instance we can see is much narrower. Why is that? Well, there were far more individuals in this study that did not have disease. Okay. So what we've done is gone from the fitted values to predictions, and then a measure of how well we've done. That is, the sensitivity and specificity estimates together with confidence limits for those two characteristics. Now, let's now move this forward a little bit more. Let's suppose that we think about now the fact that, as I alluded to a few slides ago, this cutoff is not really set for us as a strong number per se, maybe. Maybe we might argue that we should view the sensitivity and specificity as functions of that cutoff. In other words, we might ask, what about a variety of different sensitivity and specificity estimates as we vary the cutoff? And you could say, well, the cutoff could be as low as 0 and as high as 1. You could say, well, those numbers that are really close to 0 are irrelevant, and the numbers really close to 1 are irrelevant. I will come back to that in a minute. Nevertheless, we can compute what happens as the cutoff rises to the sensitivity and the specificity estimates. And what do we see? Well, as the cutoff rises, the sensitivity estimate will decline and the specificity estimate will rise. And that's what we see in this visual. So here is a graph of the sensitivity and specificity estimates as a function of the cutoff. And you can see that the sensitivity estimates decline as I increase the cutoff, whereas the specificity estimates rise as I increase the cutoff. And you may want to reflect on what exactly that means in this instance. So this is the range in which the cutoff really matters, right? Now, okay, now you'll recall that the false positive rate is in fact just 1 minus the specificity. So if we think about the false positive rate for a moment, we can see that if the cutoff is 0, then the sensitivity is 1 and the false positive rate is 1. And if the cutoff is 1, then the sensitivity is 0 and the false positive rate is 0. You could go back and look at that previous picture. So I'm making a case now which is widely seen for the understanding of the implications of this cutoff as a function of the sensitivity and the false positive rate. Very widely seen. In fact, it turns out that a widely displayed graph is one in which we graph the sensitivity versus the false positive rate. Okay. This is called a receiver operator characteristic curve. And its origins are actually, I don't believe, in health research, but in any case, they're widely seen in health research. So such a curve can be obtained. Let's have a look. And again, Stata will give us this with this simple command in Stata that's a post-estimation command it will graph the receiver operator characteristic curve in this instance. And what I'll do is add a couple of lines that I think I'll explain for you in a minute. Okay. So here is a graph of the receiver operator characteristic curve. And what are we seeing here? We're seeing sensitivity versus the false positive. So this is sensitivity estimate versus false positive rate estimate. And in fact, there is one point on this display that we have seen that corresponds to the sensitivity and specificity that we had from the use of the cutoff based on the prevalence. So that's this point right here. You can see it's well above 50%, right? Of course, it's for this particular specificity, you can see that this curve is well over this line, well above this line. Okay. So we can see that in principle, we could determine the sensitivity and the specificity, the sensitivity and the false positive rate for any cutoff ranging between 0 and 1. Okay. So the graph of this curve can be done for any candidate model. And the lines that I've drawn that where they cross correspond to the cutoff that was based on the prevalence that we saw from this study, the prevalence of coronary heart disease from this study. Okay. So the first thing we can note, and I'm not going to spend a huge amount of time on this, but clearly there's going to be parts to this curve that correspond to sensible values, but there's going to be parts to this curve that do not. They're the very low thresholds, the very low cutoffs, the very, very high cutoffs are not ever corresponding to any sensible decision as to how to determine sensitivity and specificity here. So it's the central portion of this curve that we view as having some credibility. Okay, now, nevertheless, for our purposes for now, let's suppose that we are considering the entire curve. A widely computed characteristic from all of this is something called the AUC, or the area under the curve. And in some literature, it's also called the C statistic, although I don't think that's quite as widely seen. And I'm not exactly sure of the history of the use of the label C statistic here. And part of the reason that there's a bit of can be confusion here is that there's lots of C statistics. And anyhow, we'll leave that for now. Okay, so the AUC, that's the area under that curve. And we can see that for any at all sensible models, that the AUC would be above 50%. The question is, for us, is it meaningfully above 50%? I mean, and is it judged to be a high enough quantity? The AUC is a number between 0 and 1, yes. And it's dependent on all of these sensitivity and specificity values, okay? It turns out, because the AUC is in fact a quantity that is estimated from the sensitivity and specificity estimates and the numbers that are in the numerator and denominator of those characteristics for the different cutoffs, that in fact the AUC is itself a quantity that can be viewed as an estimate of a population characteristic. I'll comment on that a little bit later. Okay. So in fact, we can compute in our case, for this particular study, we got an estimate of the AUC of 0.6546, and here we get a confidence interval for the AUC, viewed as a population characteristic then. Okay. And we've done so by fitting this model. In this case, I've done this for you for the model that includes nonlinearity. Okay. And then this ROC tab function gives us the area under the curve estimate and the confidence interval for it. Okay. Then we could say, well, what about that model where we had all of the different combinations of the age and smoking status? In other words, the model that corresponded to that stratified analysis we did earlier. Well, it turns out that if we did so, we would get a slightly higher AUC estimate. Okay. We get an estimate of 70. Here we get an estimate of a bit more than 65. Nevertheless, if we were to test the null hypothesis that these population AUCs are different, well, we get something that's potentially interesting. Again, another argument that, well, that quadratic form for the model might not be adequate at this point, right? That the actual range of different odds ratios we get is not fitting as well, perhaps, to the model we're using where I assume just this quadratic form of nonlinearity isn't doing as well as the one that assumed a different odds ratio for every age. Okay. And there's another point that I think it's on a later slide, but I'll mention it here. This test of significance I get by comparing AUCs is actually a comparison that is based on non-nested models. These two models are not nested within one another. And the likelihood, there is no directly, at least, corresponding likelihood ratio test available here. So that it, again, becomes an argument for the use of the AUC as a tool in the assessment of the comparison between two models. Okay. So the coronary heart disease smoking example was a little bit complicated, but I think at least gives you a sense of a real project and how a real project might be assessed in this using these tools. There's a simpler example I thought I would offer you now that is taken from a very fine book by Sophia Rabe-Hesketh, and it has to do with the diagnosis of heart attacks and the use of this serum creatinine kinase as a tool for diagnosing myocardial infarction or heart attack. Okay? So we might, as is sometimes argued, begin such an assessment based on a pre-assigned threshold of this this characteristic CK that is designed to presumably provide us with the background for making a prediction of a person with a heart attack. Okay. And if we did so, we see that there's quite a bit for those who have a CK above that threshold of 100 here. We get the proportion of individuals with an MI being quite high compared with the proportion that are not. And you might say, well, okay, that's interesting. Okay, and if indeed we fit a simple logistic regression with this indicator, that duplicates the fitted values we get from this direct computation of these two observed proportions in those two groups. And you can see we get the same values here. Okay. Then we could, for example, determine the sensitivity and specificity of this using the threshold of 100 as based on CK in this instance. And indeed, we get what you might say promising looking estimates of sensitivity and specificity based on this a simple probability threshold of 50%. And you might say again, well, we could have used other thresholds here. But you can see the sensitivity and specificity are pretty good relative to, for example, the last project I just showed you. Okay. And in fact, we could then display the sensitivity and the specificity as a function of the probability cutoff in this instance. And since it's such a very simple model, with whether or not the CK is above or below, we get a very simple looking picture, which I would encourage you to spend a bit of time. Understand what this dotted line here means and what this solid line means here. Put those into the correct perspective. Okay? But we could say, well, how about I was going to use the actual CK values here from this particular project and construct a similar sensitivity specificity as a function of cutoff for a model in which we use the actual CK and not just whether or not it's above or below 100. And you can see that it's starting to get a little more complicated to visualize here. But in now, it's going to be based on every time we have a differing CK value here. And there's quite a bit in play. Okay. Then we could, if we wished, compare the estimates of the AUCs from the two. And what do we get? We get that the AUC based on all of the CK values is better than the AUC based on just the threshold of 100. And the test of significance is quite leads to a p-value that's quite small. And what are we looking at here? Now the two receiver operator characteristic curves are quite simple. In the first case, where the model was based on a single threshold of 100, we get just this simple ROC curve. It's just this piecewise linear curve, right? Now, in fact, what we get for the actual is a series, again, of lines that give us the receiver operator characteristic curve. So just to kind of repeat, the receiver operator characteristic curve is just a series of piecewise linear curves. In this very simple one, it's just these two lines joined at one point. And in this example, we can see that in fact, it remains just a series of lines joined. That's a little more of the background behind what the receiver operator characteristic curve looks like. Although people call it a curve, it's actually a series of lines joined. Okay. Now, it is sometimes argued, and it is now widely seen, the AUC is widely seen in health research articles, that the arbitration about the quality of a model could be based on the AUC, and you will see that. So it could be argued here that the actual CK levels are doing a better job of prediction than the simple threshold based on the CK 100. And it's also a simple circumstance in which we can see that the comparison of these two models is is one in which we have a test of significance that's available via the AUC that is not available with a likelihood ratio test, not directly at least. Okay? So the AUC estimate is sometimes viewed, this ability to make tests of significance with non-nested models is sometimes an argument for the AUC too. Okay? But it's worth emphasizing again, going back to very early on in this session, that the AUC estimate that's computed here in any model is not based per se on any of the features of the model that we have been emphasizing in other sessions, but is merely based on the fitted values. Okay? I say merely here being a bit crabby, I guess. But the AUC estimate is based on the fitted values. Yep, that's the way it is. Oh, well, a couple more characteristics for you that I thought would be worth mentioning. And that is that, as I mentioned, the AUC is an estimate of a probability. I didn't maybe say that quite as directly here, but the AUC can be seen as a probability, and then what we get are estimates of that probability. Now, I'm not going to spend too much time into the logistics behind the interpretation of AUC as a probability. It's kind of a circumstance in which it provides us with the ingredients for seeing the AUC as a probability. Now, what is also pointed out here is that the AUC interpretation as a probability is kind of based on a game, if I may. So let's just take a brief bit of time to clarify some of that. All right. So the game is, we'll call it a game, that a case and a control have been selected for you. You're the person playing the game. And you have a classification rule. And the rule will be, well, if a person has a higher fitted value, will be assigned the sorry. Sorry. So you're going to use the fitted values here in order to make a decision as to who is classified as being the case and who is the control. So let me repeat this. I'm kind of muddling this a bit. So you're given two people. You're not giving any other information about them except for the fitted value you got from the model. But the person with the higher fitted value, you'll classify them as being the case, and the one with the lower fitted value will be assigned the control. Okay. It turns out that there's a probability associated with implementing such a rule, of using such a rule. And that is, correct classification is estimated by the AUC. Okay, in this curious little game. So, if you, with this game, assign the person as the case, to the higher of the two fitted values and the control, then the probability you're making you've made the right classification is the AUC. So you can see the AUC, we would anticipate then, for all sensible models, would be greater than 50%. You could say, well, I'm not going to, if I just merely guess and I didn't use the fitted values, then I'm going to be right 50% of the time, right? If I have no information and I merely toss a coin and guess, or guess, right? Okay. So the point being here is that the use of this little game is somewhat artificial. we have to contemplate a circumstance in which the person playing the game has one case and one control, and then you make an assignment, one to the case, the one to the case and one to the control, and getting it right is the AUC. If you used the fitted values from the model, yeah, I know. So, right, it's sort of amusing, really, but the point being here, more to the point here, is that viewing the AUC as a probability then gives us the ability to see it as a quantity that we estimate then from our data, and then we can construct confidence limits for that unknown AUC. Okay. Now, there's been quite a few articles written about the AUC in recent years. I'm just citing one paper here. There was a period of time when the AUC was just considered the cause célèbre. It was like, yeah, that's the way to do it now, folks. Well, in more recent times, there's been criticism about the merits of using the AUC, and I don't propose to take any more time here, except that anyone interested in this particular topic ought to do a literature review on the merits and demerits of the AUC and in current healthcare research. One other comment that I have alluded to but have not specifically mentioned here until now is that everything we've been doing so far makes it look like we're going to be using the data twice. We're using the data to build the model and construct the estimates, and then we're using the same data to estimate the model. Well, that's called internal cross-validation. And really, one could make the case, and again, there's quite a bit written about this, that we should really have one data set for the model building and another data set for model assessment. This is again, a very common circumstance. But I mean, the downside is that if I'm going to use only a portion, say, of the actual data available to me for model building, that I'm disadvantaging the model construction, perhaps. Maybe. Anyhow, if we have two data sets, then the process is called external cross-validation. Yeah. One other point I'll make just very briefly here, which really shows my, I guess my biases here, you could argue. But there a whole other area for the quality of model construction has to do with so-called goodness of fit. And I don't propose to say anything more about it now, except that you, as a person preparing a journal article for submission, may be obliged to offer such things. You may be obliged to offer the AUC. You may be obliged to offer other goodness of fit tests. All I wish to point out to you is that goodness of fit tests and AUC are subject to a lot of criticism. And I think there's a lot involved in this issue. Nevertheless, you need to be an educated and informed user of these tools.